pendulum on the left, which you all know, I'm sure, what a pendulum is. We have beside it a mass on a spring, like your bouncy toy. Yes, remember your bouncy toy in 4th year that you timed? Yes, remember it now? A bouncing ball. There's a football there, appropriate for July time, wasn't it? Was it Italy? Whatever. Anyway, bouncing ball. There's another example of motion. And this bottom one, which hasn't photographed very well, but it's over here, a trolley that is doing this. Okay? Yeah. Right. What I want you to do is I want you to try and work out which of those is the odd one out. There is one. And there is a reason for it. Can you discuss it in your groups and see what you think? Okay? So there is, and I'll give you a hint. It's actually something that you've not done before. So it is leading into not a new type of motion, but thinking about motion in just a little bit more detail. Okay? Something completely different. All right? Shall I just stop that there and then you can... Okay? The ball is... it's not held or influenced by something that's pulling it back to the centre each time. Yeah? Would you agree that the bouncing spring, the trolley between the two springs, the pendulum, each time they're coming back to the centre, and then maybe there's a displacement one way back to the centre, or the equilibrium, and then displacement in the opposite direction? Yep. But it's not actually tethered to the ground, is it? If it was on a piece of string, but it's not actually tethered or held to the ground. Okay? Right. That's one of the differences. What we're going to do is we're going to actually build up to this type of motion that we're talking about. It's called simple harmonic motion, or SHM for short. Has anybody heard of that? Heard of simple harmonic motion? No? Okay. So there's a basic sort of introduction to it, but we'll actually get a more scientific description of what simple harmonic motion is about. And that's the aim of what we're going to do today. We might get on to some equations about it, we might not. Okay? Now, I held up this book where Mr. Crosher was talking about differentiation. Yes? You all love differentiation, don't you? Yes? We are going to do a wee bit of that today, and I will, at some point, maybe get you to tell me what you know, but we'll maybe not do that just yet. We'll maybe leave that just yet. Okay? Right. So we'll come to that in a wee while. This thing here, now I've never done this before. I don't know if it'll work, but we'll try it. What we've got is, we have got a filter funnel. If I hold this up, you'll see that it's filled with sand, and that sand is pouring out. Okay? It is attached to the bar between the tiles. Hopefully it will hold, and we won't have the ceiling falling down onto us. And we're just going to make it swing like a pendulum. Okay? So, what's that, Chris? We're going to make a mess. Yeah, we are going to make a mess. But we're hoping to make a mess on this piece of paper. Okay? Now, what we're going to do is, as this swings, we're going to pull the paper underneath it. Okay? So that we're effectively plotting a graph of displacement against time. Okay? So, we'll start again. So it's going to go, if we swing it across the room, left to right, then we'll pull the paper that way. Right. Yeah, go for it again. Just a little swing, yeah. Okay. Do you know, I think the problem is we need to move the paper at right angles to the displacement, don't we? And it is actually going, would you say it was going that way? Yeah. Will we go for it again? Right, that's more like it. Oh, there we go. Right. What is it? What is it, Doll? Go on, say it. It's a wave. It is a sine wave, yeah? Can you see that there? Can you see that there? Yes? Okay. So that is one hint that we have simple harmonic motion, is if as we move this paper along at right angles to the change in displacement, or the displacement then change in distance, we get this sinusoidal wave. Yeah? Okay. So I have drawn some for you. These are ones that I did earlier, Blue Peach style. We have got some other motions that we could do with just if you had, say, a paintbrush and did that, you would get the same sort of shape. Okay, looks like a sine wave. Now, if I hold it that way, looks like a sine wave. Anybody add anything to Kirsten? Yeah. Yeah, starting at the maximum, isn't it? Yep, or A, or the amplitude, whatever. It's starting at maximum. Do you remember that a cosine it's like a cliff? C for cliff, C for cosine. That's how I remember it. That it dips down to start with, so it's the cosine. And if you're drawing that wave, what would you have on your x-axis? This is displacement here. Okay. Now, I've made a mistake, really, because we didn't start it from the centre point. We started it, we're saying it's like a cosine graph, yep, as opposed to a sine graph. Yep. And if I wanted you to work out the periodic time, the time for one complete cycle, I would need to give you the scale for this axis, wouldn't I? Yep. Let's say then the scale for this axis is 1 centimetre per second. So you can then label on every centimetre is a second on that axis. Yep. You could then also work out the periodic time then. If you just measure the number of excuse me, centimetres, that then is going to be the number of seconds for a complete cycle, isn't it? Yep. With me so far? Yeah. So you can write down some values for that. And you're all going to have slightly different values, that's fine. We're going to work with those. That is not normally, though, the x-axis for cosine graph. What normally is the label for it? Radians? Yes? Yeah? Or degrees, depending on how you do it. Can we go for radians? Yeah. I know you love maths. I know you do. It's my second favourite subject. I'm sure it's yours. Second favourite after physics, isn't it? Mm-hmm. Right. What is how many radians normally for sine graph? What's for a complete cycle? 2 pi. Yep. So this would be 2 pi, wouldn't it? Yeah. Okay. Now, if you pick any time along here, let's call it small t. So that's our variable time. Okay. If you picked any time along there, you could work out what that was as a fraction of your periodic time, couldn't you? Yeah. So at this point here, we would have 2 pi t over capital T. Yeah, it's whatever fraction of the periodic time is at this point here, then it's that fraction times 2 pi. Or I'll write it another way, it's that over that times 2 pi, isn't it? Yep. Are you with me? Yes? No? Not sure? Yes, it is, but we're actually going to use it, we're going to use seconds. You're right, they are equivalent, you're absolutely right, Chris, but we're going to try and use seconds. Okay? So in a minute, I'm going to try and give you a link to something that Mr. Crawshaw will be teaching you. Okay, so you're going to have to sort of bear with me at the moment. Right. Okay so far? Yeah? Think so? Right, so where did we get to? We got to that. We really can now write an equation, hopefully, for this graph. We can write an equation which is that y is a cos 2 pi t over t. Okay. Y is the y-axis, the displacement, or the displacement. Okay. Yep. It's your basic equation. Y is a cos x. That's what you would be looking at, wouldn't it? Is that not? Is that what you in maths? Is that the letters you used? Yes, it is. Right. So